Today we're going to look at probability in the sense of multiplication rules. So the previous video showed a number of steps to do probability with addition rules. Now we're going to look at a couple of multiplication rules. Now in this scenario or in these scenarios, we're going to have multiple experiments or multiple properties going on at the same time. So think of having what is the chance of having multiple outcomes or multiple characteristics. Let's think about this in a sense. So if we're picking one individual out of the state of Michigan, we could ask, well, what's the probability that somebody picked at random is over 5'6"? And then we could also say, well, what is the probability that I pick somebody at random has a trait like they have brown eyes? So we have two traits going on, and we could combine those into one experiment and say, well, what is the probability that I pick somebody out at random and they are over 5'6" and have brown eyes? So that's the type of multiple characteristics that I'm talking about. Or in multiple experiments, like what is the chance that I flip a coin twice and I get heads on both flips? Now, to understand these rules, we need to understand the difference between independent and dependent events. Independent events are ones that don't affect each other. So A and B are independent if A happening doesn't affect the probability of B happening. Okay, we'll look at some examples in just a second. Dependent events are ones that do. Like if I know A happens, then B is going to have a slightly different probability of happening. So let's think about which properties are independent and which properties are dependent. Let's go to the coin flip example that I mentioned. Let's say we flip a coin 2 times. Now, the first flip is going to be 50-50, heads versus tails. If the first flip lands on heads, is the probability changed on the second flip? Now, we should all agree that it's not. It's still going to be 50-50 on the second flip. So the outcome of the first flip did not affect the outcome of the second flip. So since these outcomes don't affect each other, these are independent events. So the 2 flips of the coin is an independent event. Now, let's look at the other one. Let's say outcome of gender and getting prostate cancer. So if I pick somebody out at random, I say, well, what's the probability that they're male? And I pick somebody out at random and I say, well, what's the probability that they have prostate cancer? Well, if they have prostate cancer, there's a very high probability that they're going to be male, right? So if I know that they have prostate cancer, that changes the chance that they're male or not. So these are dependent. The outcome of one gives me a higher or a lower probability of the outcome of the second, or vice versa. So gender and getting prostate cancer are dependent. They are affecting each other. The chance of one happening does affect the chance of the other happening. So I want you to take a minute and look at these three. One is the chance of parents being Democrats and the chance that their son or their daughter is also like-minded and considers themselves a Democrat. The second is outcome of gender and the chance that you win the Powerball. So are you more likely to win? Is your ticket more likely to win if you're male versus female? And then thirdly, the outcome of rolling two dice, those two dice landing on a 7, and then the second roll also getting roll a 7 on the craps table. So take a minute, think about all of these, push pause on the video in 5 seconds, we'll start back up. All right, so hopefully you went through that on your own. Chance of a parent being a Democrat and that their son or daughter is a Democrat, well, those are dependent. It turns out if your parents are Democrats or if your parents are Republicans, then you are more likely to be a Democrat or Republican. All right, you are more likely to have the same, you're more likely to be of a certain religion if your parents are of that religion. Now, I want to say it's not 100%. Don't get me wrong here. I'm not being deterministic here. What I'm saying is there's a more likely chance that you are. So if I looked at 100 individuals in the population and I asked their parents' affiliation, I could probably safely predict about 95% of their political affiliation based on their parents' political affiliations. All right. So dependent is this first one. This second one, outcome of gender and winning the Powerball. If I and my wife, or if my wife and I each buy a Powerball ticket, our genders are not affecting the probability that we win. If I buy a ticket, I have a 1 in, I don't know, 8 million chance of winning. If she buys a ticket, she has the exact same chance of winning, okay? Which is basically 0. So outcome of gender and winning the Powerball, those two are independent. They don't affect each other. And similarly on that third bullet point, if I roll dice and you roll dice, or let me put it this way, if I roll dice, I land on a 7. So when I say land on a 7 in craps, the game of craps, for those of you who don't know, you roll 2 dice. And you look at the sum of the numbers on the dice. 7 is a particular interesting number in craps. So if the 2 dice add to a 7, that means something. So if I roll dice and the 2 dice add to a 7, and then on my second roll, the exact same probability of landing on a 7 is going to exist. So the first roll and the second roll are not affecting each other. So these are independent events. And generally speaking, on all of the games in the casino, when you start fresh, that's a new independent event, okay? So if you're playing craps, you roll the dice, you pick up the dice, the same probabilities exist. You roll the roulette wheel, second roll, the same probabilities exist. You play cards. Now, if they gather up all the cards, reshuffle the decks, play it again, the same probabilities exist. So independent or dependent. Now we're going to focus on independent multiplication first, okay? It turns out that there's a really simple rule when we have independent multiplication. If two events, which we call A and B, are independent, then the probability that both happen is simply the probability that the first happens times the probability that the second happens. So all we have to do to find, well, the probability of A and B both together happening is multiply the probabilities together as long as the events are independent. All right, so let's take a look at an example here, specifically the roulette wheel. Now, if you look at the roulette wheel, basically, well, let me take a step back. Our roulette wheel that we're going to use in this class is going to be the 38 slot roulette wheel. Some of you, there's actually two different types of roulette wheels. One is a 37 slot roulette wheel, one is the 38 slot roulette wheel. So we're going to use the 38 slot roulette wheel. And the 38 slot roulette wheel has 38 different numbers. They have the numbers 1 through 36, plus they have a 0 slot and a double 0 slot. So we have a 0 slot, a double 0 slot. Notice that both of those are green. So the 0 and the double 0 are green. So we have two green numbers. And then the 1 through 36 numbers are all either black or red. So half of them are black, half of them are red. So 18 black, 18 red, and 2 green on the 38 slot roulette wheel. So here's what we're going to do. We're going to ask, well, what is the probability of getting 2 rolls on the roulette wheel and both are double 0? All right, so the chance of getting 2 rolls that are both double 0. So we have to think back to our fact that rolling 2 times on the roulette wheel is an independent process, right? So we go back to the independent multiplication rule, and it says, well, if you roll 2 times on the roulette wheel, I can just multiply the probability of getting double 0 once times the probability of getting double 0 on the second time. All right. And then obviously, because double 0 is one of our slots, what we're going to do is we're going to take, and let me do this on scratch paper here, to find the probability of double 0 on roll 1 and the probability of double 0 on roll 2. I would take 1 over 38 and then multiply times another 1 over 38. Now, if you're having a difficult time saying, well, why is this 1 out of 38? Well, double 0 we said is 1 slot. We have a total of 38. So we're using classical probability to say that, well, rolling double 0 once is a 1 in 38 chance of success. Rolling double 0 a second time is also a 1 in 38 chance. Just as a side note, this is how I typically denote it. I typically denote it, well, double 0 on roll 1. I just put a little subscript of 1 there. And double 0 on roll 2, I just put a little subscript of 2 there. So that's how I denote it. You don't have to, but that's how I do it. Now, we've set this up. So now we know that the probability of the first thing is 1 in 38. Probability of the second thing is 1 in 38. We know they're independent, so the probability of both things happening is going to be just the product of those two fractions. So we multiply the fractions. Hopefully you remember how to multiply fractions. 1 times 1 is 1. 38 times 38 is 1,444. So the answer would be 1 over 1,444. Okay, so that is the probability of rolling double zeros twice in 2 rolls on the roulette wheel. Okay, by the way, if you're doing this in Moodle, Moodle is going to require you to round things to 4 decimal places. When you put in 1 divided by 1 over 1444, it turns out that you actually get a scientific notation answer. So what you'd have to do is you'd have to write the scientific notation 6.93 times 10 to the negative 4th. If you're wondering what that number is, that number actually is 0.000693. Again, you don't, for purposes of the test, you can leave it as a fraction. If scientific notation comes up on Moodle, I'd probably ask you just to put it in scientific notation. It in this section it does not, but if it did, I just have you put it in scientific notation. You don't have to write the decimal or anything like that. So 1 over 1444 is the probability of getting a double zero on roll 1 and a double zero on roll 2. Okay? I want you to take that principle and try to answer the next two questions. So push pause on the video, and in 5 seconds I'll come back and explain that. All right, so hopefully you push pause on the video. The first question says, what's the probability of getting black on the first roll and red on the second roll? Let's go back to my scratch paper here. So we're asking for the probability. Whoops. Let me just do it this way. Copy and paste here. So what's the probability of getting black on the first roll, then red on the second roll? That's how I denote it. B on roll 1, R on roll 2. I think that's what the question said. Black on roll 1, red on roll 2. Okay. Now, black is 18 out of 38 slots. Red, there are 18 reds out of a total of 38 slots. So if I'm just doing the multiplication straight, 18 times 18 is 324. 38 times 38 we already saw was 1,444. Now, I do want to say, again, you can write this as a decimal. If you wanted to write this as a decimal, round it to 4 decimal places, 0.2244. And also, if at this stage on your calculator, you wanted to put this into a fraction, it turns out there is a reduced form fraction you can have. Now, again, I don't want you to reduce your fractions. There's no need to do that. We saw that you don't need to reduce fractions in the previous video. But if you did reduce fractions, I would not count that against you. If you gave me 81 out of 361, that's fine too. Okay? So I'm okay with either the unreduced fraction answer, the decimal answer, or the reduced fraction answer. I guess I'll write right now the reduced fraction answer, but again, you do not have to reduce the fraction or anything like that on the test. All right, so if you want to write 81 out of 361, that's fine with me, but it is not a necessity. You can either write it as that. Moodle is going to require you to round things to 4 decimal places, so Moodle would expect you to write 0.2244. But I am perfectly fine with the 324 over 1444 as your answer. All right, let's look at that last problem. What's the probability of getting red on roll 1, then green on roll 2, and then another red on roll 3? So now we have 3 rolls, but you can imagine that the same principle holds true as it did on 2 rolls, will hold true on 3 rolls as it did on 2. So you've already calculated this, hopefully. I'm going to go right into the calculation. So probability of red, green, red. All I would do is say, well, red is 18 over 38 times green, there are 2 slots, so 2 out of 38, times another red, well, another red is still another 18 out of 38, and we multiply all those together, and if you take 18 times 2 times 18, I'm doing this on my calculator, you get 648. If you take 38 times 38 times another 38, you get 54,872. So 648 out of 54,872. You can reduce that to a decimal if you'd like. If you'd rather write that as 0.0118, rounded to 4 decimal places, that's fine. You could have also reduced the fraction. I'm not going to reduce the fraction because it's not necessary. So either way on the test is fine. If you have unreduced fraction, if you have your decimal, if you have your reduced fraction, all of that's fine on the test answer. On Moodle, it's going to ask you to round a decimal to 4 decimal places. All right, so that's the basic concept of independent multiplication. Now, we can do some other interesting stuff with independent multiplication, not just what's the probability of getting A, then B, then C, but we can ask questions like this. What's the probability of rolling 5 times and you never hitting a red? So maybe you're thinking about, well, let's go game the system. All right, I'm going to bet on red, and then if I lose, I'll just double my bet on the next one. And then if I lose, I just double my bet and then get the next one, and so on and so forth. And eventually we're going to hit a red. But maybe you only have a finite amount of money, so you can only play 5 times. So what's the probability that I roll 5 times and you don't get a red, or I don't get a red? Now this one's a little bit more in depth, all right? Not getting a red, rolling 5 times. So let's think about this. Not getting a red, but we're rolling 5 times. So when it says never get a red, I don't want a red. So let's call N not red. Okay? So I want to get a non-red on the first roll. And then I want to get a non-red on the second roll. And then so on and so forth. I want to get a non-red on the third roll. And I want to get a non-red on the fourth roll. And I want to get a non-red on the fifth roll. So it's a fairly straightforward concept. We're going to get not red 5 times. So what's the probability of getting not red on any of those rolls? So let me put it this way. What's the probability that I don't get red on a single roll? Okay, we know there are 18 slots that are red. We know there are 38 total slots. That means there are 20 slots that are not red. So if we're thinking about a fraction, what we would do is we would say, well, non-red takes into account 20 out of the 38 slots. And so we would multiply that times itself. Something's going wrong there. I apologize. There we go. So we would multiply that by itself 5 times. Let me write that. By the way, you can imagine if we said, well, let's not get red 17 times in a row, you probably wouldn't want to write all those multiplications. You'd rather probably turn that into an exponential problem where we just said, well, let's just take my fraction, which is 20 over 38, put it in parentheses and raise it to the exponent of 5, okay? Now, by the way, be careful. You must put this in parentheses when you're typing it into your calculator, or if you don't, it'll just take 38 to the 5th power, all right? So make sure those parentheses exist when you go ahead and do that. Now, what I got as a decimal was 0.0404, and we'd stop there on Moodle. If you wanted to try to make this a fraction, it turns out it's a gigantic fraction. So I'd probably just leave that one as a decimal. 20 over 38 to the 5th power becomes that. And again, that's really useful using exponents rather than repeated multiplication when you have a lot of trials. Like in this case, we have 5 trials back to back to back to back where we're rolling the roulette wheel. Okay, so basically what I'm doing there is I'm using complements on an individual trial, okay, the not rolling red. Now let's go to this next question. What's the probability of rolling 4 times and getting at least 1 green? All right, what does at least 1 green in 4 times mean? Well, think about this in terms of sequences. So if my sequence were 4 greens in a row, that would be at least 1 green. However, you could have gotten 3 greens in a row and then a non-green. Let me make these the same size. Now, I know I'm switching my notation a little bit. N was standing for non-red up here. This new problem, we're trying to find the probability of at least 1 green. All right, so new problem, N is going to stand for non-green instead of green. Okay, notice that's not the only sequence that has at least 1 green. In fact, you could have gotten green 3 times in 4 different ways. You could have gotten the non-green in the last spot, or in the 3rd spot, or in the second spot, or in the very first spot. Okay, all of those are different ways to get at least 1 green. Now, at least 1 green, that's not all. That's not all the ways to get at least 1 green. We could have gotten 2 greens. 2 greens would have been at least 1 green. And we could have gotten those 2 greens right up front. We could have gotten those 2 greens in the middle. We could have gotten green, non-green, green, non-green. We could have gotten a non-green in the front, and then green, green, non-green. So there's a lot of ways to get 2 greens and 2 non-greens. So here's all the ways to get 4 greens. Here's all the ways to get 3 greens. Whoops. There, 3 greens. Here's all the ways to get 2 greens. And at least 1 green could have also gotten 1 green. So you could have gotten green and then 3 non-greens in a row. The green could have came on the second. The green could have came on the third. The green could have come on the very last roll. So all of these sequences fall into the category of at least 1 green. So if I were to calculate the probability of at least 1 green directly, I would have to find the probability of every single one of these sequences, just like I did up here, just like I did up here. And because each of these sequences is different, I would have had to add all of those up. Now, what you'll see, hopefully, or what you have seen maybe already, is that there's one thing missing here. What's the complement of at least 1 green? Let me move that up. What's the only sequence that we don't have? And it's never getting a green. So the complement of at least 1 green is not getting a green 4 times in a row. And what do we know about the complements? So the complement of at least 1 is never getting 1. All right? And what do we know about the complements? Well, we know that the probability of an event plus the probability of the complement add up to 1. We saw that in the last video. So what I can do is I can find the probability of never getting a green. By the way we do that, well, what's not getting a green on the first roll? Since there's 38 slots, there's 2 green slots. You do 36 out of 38 times another 36 out of 38 times another 36 out of 38 times another 36 out of 38. Okay? Or again, if you wanted to, you could put, I'm going to type this into my calculator as 36 over 38 to the 4th power. Okay? And that comes out to 0.8055. Again, I'm typing that into my calculator, 36 over 38 to the 4th power. Now, we're not done yet. Okay? What we just found is that the probability of the complement of what we were looking for is 0.8055. However, we wanted to find the probability of the event. So the probability of at least 1 green, we know that this probability, the probability of at least 1 green, plus the probability of its complement have to add to 1. So the way we can calculate it is we can take 1 minus 0.8055, and what that does is it ensures that this probability, the probability of at least 1 green, plus the probability of the complement have to add up to 1. So the probability of at least 1 green is 0.1945. And there you have it. And this is what I was talking about in the last chapter, where we said, well, sometimes the probability is a lot easier to calculate from the complement, standpoint, and then just take 1 minus that number and find the probability of the event I was looking for. Notice that this is just one multiplication and then 1 minus that result, rather than having to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different multiplications, and then adding them all together. And by the way, that's one that you'll see, something about probability of at least one of something. You'll see that in a couple of different contexts. So we're going to use another problem, another characteristic, another place where a lot of times you see independent multiplication. So we've seen independent multiplication with like casino games or roulette, for instance. But it turns out independent multiplication we can also use, we often use, when our population is fairly big. Okay? So this is what I mean. Let's look at this problem. It says, according to Pew Research poll, about 6% of Palestinians had a favorable view of ISIS in the year 2015. So if we went back in time into 2015, what would the probability be that if I select 5 Palestinians, I find at least one with a favorable view of ISIS? Now, 6% is the probability of being favorable view. We want to find at least one who has a favorable view of ISIS in a group of size 5. Now, here's the deal. There are, I don't know how many Palestinians, but millions. Okay? You can look up the population, or those who claim to be Palestinian, and it's probably, I would say, in the millions. All right, so I just quickly looked that up, and it's in the millions. There's millions of Palestinians. Now, here's the deal. If I remove 5 from the population, that's not really going to change any probabilities in there, or it's not going to change that 6% in any significant way. So because I have such a large group, picking one person from Palestine, and then picking another person from Palestine can be considered independent events. Okay? Again, they're not truly independent because after I get person A, I can't pick person A again, but it's not going to change those numbers at all. It's not going to change that 6% number. All right? So, according to the research, 6% of Palestinians have a favorable view of ISIS in 2015. So if I went into 2015 and picked 5 Palestinians at random, what's the probability that one of them has a favorable view of ISIS? Or at least one, I should say. Again, notice the connections between this and the previous problem. Very, very similar. Okay, let's think of this. So the probability at least one is favorable to ISIS. Now I'm not going to write the entire thing out every time. I'll probably just say favorable F, not favorable N, or something like that. And you can imagine in a very, very similar way to what we had before, at least one green in our previous problem, at least one favorable. There's a lot of different sequences with one favorable and some that aren't. So instead of doing this directly, this is one that it's better to do the complement. So what is the complement? Well, the complement is that none are favorable to ISIS, right? So the probability that none are favorable to ISIS, so not favorable on the first pick, not favorable on the second pick, on the third, on the fourth, and on the fifth, okay? Notice again, this is the probability of the complement, so be careful here. What do we say? Well, 6%, if you recall, have a favorable view of ISIS. And how many then would not have a favorable view of ISIS? So 6%, each individual is 6% favorable. I should say, has a 6% chance of being favorable. That means they have a 94% chance of being not having a good view of ISIS. All right. So 6% have a good view of ISIS, 94 do not. 94% do not. So in a very similar way to what we just did earlier, we would say, well, 94% don't. So if I pick one, my first pick is going to have a 94% chance of not liking ISIS. My second pick is going to have a 94% chance of not liking ISIS. And so on and so on and so on, 5 times over. So we're getting 0.94 multiplied times itself 5 times. In other words, 0.94 to the 5th power. And we can just type that into our calculator. 0.94 to the 5th power is 0.7339. Now remember what this was. This was the probability that none were favorable to ISIS. That's not what the original question asked. It said, what's the probability that at least one is favorable to ISIS? So what I would do is I would take the complement of the number that we just found. So 1 minus 0.7339. And the probability that at least one has a favorable view of ISIS is 0.2661. So this is how it works, right? We have this trait that's not a very common trait among Palestinians. 6%, the vast majority of Palestinians don't like ISIS, but 6% do. And if we pick 5 Palestinians, well, while each one has a 6% chance of liking ISIS, so each one individually does not like ISIS, has a very good high chance that they don't like ISIS. Well, if you put 5 together, you have about a 26-27% chance that one of those people do like ISIS. Hopefully that all makes sense. Let's take another example. I want you to try this on your own with just some bigger numbers. So we'll start with the same scenario. We're going to assume, oh shoot, we're going to change the numbers. So we're going to start with the exact same scenario. We're talking about picking a certain number of Palestinians and seeing if they like ISIS or not. But we'll ask this question: what is the probability that if I select 3 of them, all 3 have a favorable view of ISIS? And then once you try that one, you can move on to the next problem and say, well, what's the probability that if you select 50 Palestinians, I find at least one who has a favorable view of ISIS? So try to answer those 2 questions, push pause, try to do this by yourself, and then in about 5 seconds I'll come back and show you how both of these problems are done. All right, so let me start with the first one, okay? We're doing independent multiplication. I say, what's the probability you pick 3 Palestinians, all 3 of them like ISIS? All right, so I'm picking 3 Palestinians. Let me scroll down to a new page here. What's the probability that all 3 have a favorable view of ISIS? So I go favorable, favorable, favorable 3 times in a row. Maybe this looks a little bit better, I don't know. So what is that? That's 6%, 6%, 6%, 3 times in a row. So actually, let's do this first. By the way, hopefully you guys don't have any problems converting percentages and proportions now. We've done that a few times, so I'm not spending a whole lot of time on that. But basically, I take 6% 3 times in a row, and again, this is one of those scientific notation outputs. It's 2.16 times 10 to the negative fourth. All right, so the chance that I pick 3 people and all of them like ISIS is very, very low, right? If you'd convert that to a decimal, it'd be 0.000216. All right, so that is a very, very low chance that you pick 3 people and all of them like ISIS. All right. Next problem says, what's the probability that out of 50, so this one is out of 50, what is the probability that at least one has favorable to ISIS? All right. So what we're going to do is find the probability of the complement. And remember, at least one, the complement is that none are favorable to ISIS. Oops. So what we would do, none favorable to ISIS. Again, not being favorable to ISIS is a 94% chance. So again, the vast majority of Palestinians do not like ISIS. So what's the probability that every single one, all 50 of them, dislike ISIS? So 94% dislike ISIS. So we'd have to do that 50 times in a row. Now, this is obviously one you're going to need your calculator for. And notice that I'm not writing n because that would just take too much time. I'm not writing 0.94 times 0.94 because that takes too much time. This is one that you're going to need your calculator and exponents for. But what I got is about 0.0453. All right. Now again, that's the chance that none are favorable to ISIS. That's the complement of at least one being favorable to ISIS. So notice that individually, each Palestinian has a very high chance of disliking ISIS and has a very low chance of liking ISIS. But when you take a group of 50 Palestinians, it's actually fairly likely that you're going to find one person in that group, again, randomly picked, who likes ISIS. all right, you have about a 95, slightly over 95% chance that at least one likes ISIS. And this should um, make sense to you. This would also work with the roulette wheel, right? You have a low chance of winning, but if you played all day, you're definitely going to win some of the spins. You play all day and you bet green, you're definitely going to win a couple of those spins. But, over time, obviously the probabilities are against you winning more money than you lose. So you're obviously going to hit some greens sometimes, but a lot of times you're not going to hit greens. So this is how low probabilities work. So a low probability event, if it happens over, or if that same um, experiment happens over and over and over again, it's very likely to come out at one point. Now, you might ask, well, why did I use this example? And again, it harkens back to chapter 1. All right. People oftentimes using examples with ISIS or Palestinians in it, it invokes controversy, or it invokes people thinking about, I don't know, differences between religions or stuff like that. And just like I said in chapter 1, none of this is controversial data. Okay. One other thing I want to say about this idea of independent multiplication. So we've seen the roulette wheel and we've seen this ISIS example, is that if I ask you about finding these probabilities, I'm going to give you the information like 6% have a favorable view of ISIS. I'm not going to expect you to know that number. Similarly, when we deal with the roulette wheel, if I talk about, what's the probability of betting black or green or red, I'm going to tell you in the problem that there are 18 black slots, there are 18 red slots, and there are 2 green slots on a roulette wheel. Okay, so I am going to explain, or I will state that stuff in the context of the problem, just like I would if I ask you a question about rolling a die, or I said rolling a die, you should know that there's 6 sides on a die. But if I ask you about picking a card, things of that nature, I'm going to give you, I won't give you a picture of the roulette wheel, but it'll say like, hey, there are 18 black slots, 18 red slots, and 2 green slots on the roulette wheel. Now find these following probabilities. All right, so that's my independent multiplication part of chapter 3. And then we'll start up the dependent multiplication stuff in the next video.